bit. So get started. To begin, I'll do an acknowledgement of country. I guess you guys are not seeing the screen.
I can do an acknowledgement if you want.
Yeah, right. Okay. We acknowledge that we're on the lands of the Wurundjeri and Boer peoples of the Kulin Nations who have been custodians of this land for thousands of years, and acknowledge and pay our respects to the elders past and present. We extend our welcome also to the traditional owners of the land from which people on.
I think the speakers inadvertently muted themselves.
They can't hear me?
Can hear.
Can you hear me online?
And now,
Yes, we
thank you.
can now. Yeah.
Okay, I'll just speak a bit louder. Yeah, we have a new council member, Alex, who's joined us as Deputy Communications Officer. So yeah, this is our council for the year, and if you see any of us around, please feel free to say hi. And for those of you who are new here, this is our talk a little bit about branch. We have the Stat Society website for Victoria branch. We should rename that to Victoria, Tasmania. Our branch email is vic.branch@statsorganisation.au. We have moved on from Twitter or X now. We're on LinkedIn, so please give us a follow. SSA Victoria and Tasmania. And we have a meetup group. A little bit more about membership. We have student membership for $20, which is really worth it. We're running a scholarship scheme soon, so stay tuned for that and look out for more details. Full membership for normal members is $265 annually, and we have discounts for recent graduates, ABS employees, and retired members. For more benefits, you can go onto the website. We have a lot of discounts for books and other things, actually. Yeah, so we'll visit. And a little plug for our upcoming events. August 20th of August, we have seminar on causal inference and machine learning with Daisy Shepherd. That will be in RMIT, in CBD. We have a social event coming up. The date is to be confirmed, but that's in August. We're going for bowling, and that's in CBD as well, Kingpin Crown. Without further ado, I'm going to introduce our speaker today. And also we're going for dinner after this. For those of you who are in person, we're going to Kimchi and Bap, Korea, which is nearby. So if you want to follow, just let me know. They don't take book, which is not long. Okay, so I'll introduce our speaker, Carolyn from CSIRO Data 61. Carolyn Huston is a senior research consultant at CSIRO with a background in statistics who enjoys applying statistical thinking from data design, modeling, reporting on uncertainty, etc. to real-life problems where results and methods will be used. She has led multiple projects related to bushfire resilient planning, particularly in the domain of improving electrical network safety. In addition to bushfire commercial work, her work requires a keen interest in understanding how to improve the uptake and effectiveness of AI as a complex model in real-life decision-making. As a consequence of this interest, Carolyn is currently performing more formal research in responsible innovation and operationalization and dissemination of equitable AI tools in a trusted and defensible way. She is currently the digitalization lead of CSIRO's Smart Energy Mission, where energy transition has many interesting AI challenges and opportunities in both data science and responsible innovation. Carolyn is also an officer and chair of the Data 61 Diversity, Inclusion and Belonging Committee and the Analytics and Decision Sciences Representative for Reconciliation Action Plan Activities and Reporting. And today she'll be talking to us about explainable AI and different types of graphs. Hand it to you, Carolyn.
Okay, can people still hear me? If somebody can give me a thumbs up online, I'm trusting that people in the room can hear me. Okay, got a thumbs up. Okay, now I'll try sharing my screen. I'm gonna get this screen. Okay, it should be sharing, and I'm going to pop up a PowerPoint in just a second. We've already done a welcome to country, so wait. Yeah, there we go. And I'll put it in presenter view. So you can actually see something. Can everybody online see that okay? And I'm counting on Swen to tell me that they're giving me a thumbs up or indicating that they can't see. Yeah, so as Swen did her very kind introduction, I'll be talking to you today about explainable AI and different types of graphs, a little bit overlapping, but mostly sort of sequentially as two topics that are interrelated but different. We already had a lovely acknowledgement of country, but because I'm not always in the universities and in the statistical society, I thought I'd give a bit of a background as to who I am. So I started my life in CSIRO as a statistician, and as I've talked to some people around here, sometimes organizations get reorganized. So I've also been labeled as a data science, big data specialist. And of course, machine learning and statistical machine learning. And I'm actually sitting in a statistical machine learning group at the moment. But in Data 61 right now, we are all about being AI, right? And explainable AI is the corner of AI that I feel most comfortable speaking to. So that's kind of where I'm doing some work. So as much as I started in statistics, I've had a few rebrands through time. And it's also given me the opportunity to talk to researchers in these related but different fields to statistics. And I know I sometimes feel frustration because I'll look at machine learning algorithms and I'll say, this is just statistics rebranded. You know, they're calling something post hoc explanation and I'm calling it goodness of fit. And they're calling something, or I'm calling something sampling and they're calling it algorithmic bias. And they're talking about their transparency of models and I'm talking about inference or post hoc explainability. So there's definitely a benefit to talking to each other and having a shared language so that you can benefit and leverage from the different research that's happening in those domains. Because as much as statistics is, of course, the best domain, it is not the only one, and other people do good stuff too. And the other area I'm working particularly for applications is with what's called the Smart Energy Mission at CSIRO, which is a big collection of projects that is trying to coordinate or help coordinate energy transition. And from my side of things, particularly from a digital perspective, and understanding both some of the algorithms that are involved, but also understanding what are the human impacts of some of those changes. And again, like I said, I'm a statistician at heart, but because I've had to work with these different people, I've had to come up with my own construct of the world as to where statistics and machine learning and AI all sit with one another so that it makes sense to me. So I'm going to draw you a picture, which is a very non-representative Venn diagram. So don't get mad that my overlaps aren't correct. But statistics has a different focus to, I think, machine learning, even when the algorithms are the same. So to me, one of the things that is special about statistics is we're really focused on inference, right? So that's really an important part of our model is you understand part of the world based on what you've done. And that is the explainable part in machine learning or AI. And another really important area that statisticians have courses and they talk about a little bit is things like populations and samples, where the data come from. Okay, and again, I think this is a slightly different focus and flavor than we get in a purely machine learning focused environment. But machine learning does great things too. They're really good at making repeatable predictions, and they've, in a sense, grown up and become popular in a time when we have lots of compute. So they can throw lots of algorithmic compute and things to do things like pattern discovery and neural nets and things that weren't available before. But then all of us sit together under an umbrella that we're currently really living in Data 61, especially, which is AI. And AI is an engineered system that might include these machine learning and statistical models as components. And if you disagree with me, you should put up your hand and shout it out because I love a good debate. But it's this engineered system that contains the models. It tends to mean that the models are not just sort of prototypes and they work as concept, but they have to be scalable, right? So that's ChatGTP. It's got a lot of probabilistic models in it, but it is scalable and we're all using it and they're building servers so that we can keep using it even more. And it tends to be automated AI. So things like updating the models or the data collection, those processes are quite often automated. So once they're in there, sometimes it's a bit set and forget. Which means for me as a statistician who really cares about that in population and the samples, those things can get a little bit stuck. Yeah. And of course, the big cool things that we hear about in the news all the time, which we will definitely talk about and have a few giggles, are things like ChatGPT. But there's also been AI prior to that, where they, things like bank loans. Those things get used in the service environment at a broad scale. So we see that there is this, and I don't know if people can see my mouse, so I won't use it. We've got this sort of data to models to production software to society, where we're all on this pathway to impact. So I want to take some of these ideas about stats and ML and AI and kind of reframe them in the context of an example, because when I was thinking about doing this talk and some other talks that I've done, I thought, I just wanted to sort of demonstrate a simple regression line, because everybody knows what it is, and it's so simple to demonstrate around. I thought, I don't want to write my own R code. Surely if I go really quickly, somebody will have written the R code that does this the way I want. And I was reading some of these blogs on how to do a regression, and they write the regression line here. This is a regression line. We can all agree this is a regression line, I hope. Sometimes I've read it like this, pretty fancy. There's a summation in there instead. And that's kind of where it stopped. And I had this, moment, because that's different to how I remembered learning in statistics, and what, in terms of what the emphasis was. Because the first two equations, we're seeing an equation, which means in a way that they're quite focused on prediction. And I must admit that the majority of the blogs I saw were framing regression as a supervised learning, not necessarily as a statistical method. And then there's this end bit, this little bit here, that was missing, that was talking about the distribution of the errors and how they were formed. And we're like, well, why is that important, Carolyn? That's not a very big addition. But to me, it is, right? Because when we talk about something being identically and independently distributed, we're talking something about where the data came from that we're using to drive this prediction model. And we're talking about maybe the sampling methods that we think can give us that identically and independently distributed data, like simple random sampling or some other sort of random sampling approach. We're going in here and we've got this distribution where we're talking about the uncertainty in our prediction, which is, again, something that gets lost sometimes when all we're focused on is the narrow prediction itself and how well that is working. And there's even goodness of fit components when you think, well, this is telling me I think my errors are normally distributed, because they don't have to be normally distributed, do they? So I'm telling people a lot of what I think about my assumptions, where my data comes from, what I think it's like. And you can see that kind of, when we look at that and we evidence it, we can say, okay, we've got confidence intervals. We can see that there's spread of data where we may or may not have normality, but I can test against those things because I've made that explicit, even if it is in this kind of, notational way. So I think it's really important, that statistics brings that last little articulation to regression models and to a lot of the other modeling that it does, because it's where some of the flaws happen when we look at the stuff that ChatGPT gets wrong, or we get wrong when we're giving people bank loans, is some of that data process and some of that error process. All right. And now I'm going to dump you into this world. I've told you all, if you're into statistics, you're kind of special, these special things. But there's all these contemporary things happening in the world, and ChatGPT is just one of them. But as we have more ChatGPT and more applications of these AI systems in the world, ethical AI has become a thing, and responsible innovation has become a thing. And I think statistics has a lot to contribute to these conversations, but I'm not hearing a lot of statistical voices sharing their views in that forum. And partly it's because we're not getting asked, and partly because it might be that we're not fully aware of what's happening because we're not all AI specialists. So I got kind of dumped into that world. In a good way, it's been lovely. But for those of you who don't know, Australia has an artificial intelligence ethics framework. Okay, so it's the framework that quite a bit of research around ethical innovation in this kind of data space takes place around. And when we're thinking about that whole AI system that we're building, it's supposed to align to some of these principles. And when I look at these principles, I can really see that there's a role for stats to be better heard. And there's also opportunities for stats to think about, hey, maybe we need some new contributions and new research so that we can align to where the world is now. So I'm just going to run through them quickly so you see them, but if you Google Australia's Artificial Intelligence Ethics Framework, you will no doubt find it posted on the government website. But the first one is human, societal, and environmental well-being, that AI systems should benefit individuals, society, and the environment. That feels very Isaac Asimov. I don't know that there's something specifically statistics about that other than, we've all got integrity as human beings. But then we get into things like human-centered values, that AI systems should respect human rights, diversity, and autonomy of individuals. Some of that can be done through thoughtful sampling, right? Do we need to sample everybody or just some people so we're not exposing everybody to those experiences? We can start to think about how our tools can help answer these challenges in ethical AI development. There's privacy protection and security, so AI systems should uphold privacy rights and data protection and ensure the security of data. And again, the algorithms we use, how we can deparse or not deparse the data, I think there's a role for statistics to play in there. I remember going to a lecture by Louise Ryan, and she was talking about, they were giving a whole bunch of the raw data when they could have just used the sufficient statistics, right? And then we're completely obscuring who the people are in the system, but we're getting completely accurate results. And then there's things like reliability and safety, like AI systems should reliably operate in accordance with their intended purpose. I think this is probably a good area for us to think about developing work, that statistics could be better as a discipline at understanding how our models get used in the world in systems like ChatGPT. What is the life cycle, the AI life cycle of the model that we're building? I might be building the prototype, but how's the next step in line going to be using this? Does the model need to be updated over time? And that's something that I should make sure is very clear when I hand over that piece of work. Should the updates be managed in a way so that the data are consistent through time, or are we expecting that that's going to change? Those are things that we need to think about and plan into, and I think we could discuss better as a cohort in statistics. How do we do that better so that our methods and models get used in a more ethical way? All right. And I think we get to this second set of 4, where I think it's a lot easier to see where statistics might be involved. Things like transparency and explainability, and I think I've already touched on the fact that we do inference pretty well. It's not the main focus in machine learning, but it is a big focus in statistics, so we do it quite well. So there should be transparency and responsible disclosure, so people can understand when they are being significantly impacted by AI and find out when it's engaging with them. That's part of it. But if you don't have the explainability of the model, you don't get the contestability portion, which is when an AI system impacts a person, community, or environment, there should be a process that allows them to challenge or use the outcomes. If they don't understand those outcomes, if they don't understand the potential flaws in data collection, if they don't understand the inference of the model or how the model works at least a rudimentary level, they can't contest the system, and that becomes very unfair to those who are in the tech know and those who aren't. And accountability, again, this is speaking to what I talked to earlier, is people responsible for different phases of the AI lifecycle should be identifiable and accountable. So where we are a piece of that lifecycle, I think it's good to identify ourselves and claim both the good work that we do and what we think is responsible use of the tools that we're creating. So that's a bit of a call to action there. I think this stuff is really cool because, every statistician I've worked with has had a heap of integrity, and I think that we can bring that to this AI space as well. And now I'm going to zoom in a little bit and talk more about transparency and explainability, because I've had that role in explainable AI and explainable machine learning methods. So we'll start this off with a colleague I had was talking to someone in another part of CSIRO, and they introduced the idea that perhaps what was needed was an explainable model to help them solve the problem. And the response we got was, not another explainable model. That is not what we need. So there's a bit of a gap, isn't there? There's a difference between what I, as a statistician or a machine learner, was bringing into that conversation, or my friend was bringing into the conversation as explainable, and what was explainable in the context of a researcher in an applied discipline. So there's this even bigger difference between what is understandable and accessible and explainable to people with data science, statistics, machine learning backgrounds, and the general public. So I'm going to argue that responsible AI and ethical AI and trust in AI requires in-context transparency and understanding of models, which isn't necessarily, we are a context of relatively educated people around data, but there's a lot of context where we can't assume that knowledge is there. And then this other thing that I have a lot of fun with, which is the idea that transparency of a model might not mean the same thing in a context that it does to a machine learner. So we have to mind the gap, because all of us, not just the data scientists, need to understand, trust, and manage the AI and the models and all of that digital stuff in our lives. So I propose, I've made these new friends in the design department at CSIRO, I propose taking a bit of design thinking thoughts and bringing it into data science. And maybe it should be a new branch of explainable machine learning. And I've read some books around this, and they've got some exciting ideas, and I want to take you through three of my top ones, which are ideas around what is an affordance, what is a signifier, and what is a cognitive model, and how we can use that when we are thinking about developing and explaining our own models, not necessarily to the stats crowd, but to everybody else out there. And I've given you a picture of a car because a lot of people really feel strongly about their cars. They might hate their car if it's got a window that doesn't roll down. They might love that V8 engine that goes vroom. They might be techie and think, my car is a walking computer, I'm so excited. But this piece of design technology invokes a feeling in them. And in design, good design is about taking a thing and not just conveying what its technical capabilities are, but in invoking an emotion about using it, so they use it in the way that we want, or buy the thing that we want to use it in the way that we want. So maybe we can bring a bit of this good feeling that people have about rooming their engine and bring that to explainable AI and statistical models, so people don't make sad faces at me when I say, let's bring an explainable model to this situation. So an affordance. An affordance is about what actions are possible. And those actions can be possible with a tool, an object, or a model. And it's only recently that design thinkers have started looking at how that fits into the digital world. But if we think about a chair, maybe this chair, not the ones you're in, it has the affordance of I can sit in it. And that's probably the desired one. I could also stand on it to change a light bulb. If there were a fire, I could use it to crash a window. So there's all of these things that you can do with a chair. They might not be its primary purpose, but we can do them. So it's what actions are possible. I will argue there are some non-productive affordances. It has been school holidays, and my daughter is supposed to have this craft project of making cute bracelets for all her friends. And we got this toy. And it's really difficult to use because it's got all these pegs, and if you happen to get your elastic bands going the wrong way and you don't put them on in the right order, the bracelet doesn't turn out. You just have springy elastic bands everywhere, and your kid gets upset. So there are lots of silly ways we found to use this when we were upset with it. It can be, you can take it away and use it for hair elastics. You can use it to whack something. If you're really mad, you can even try and flush it down the toilet. But I would argue just because my daughter could do these things with her toy doesn't mean you should. And that's quite often true with models as well. So one of the ways we can help guide people, and there's somebody named Jenny Davis who I've worked with at the ANU around how to use digital technologies correctly, is through using something called an affordance framework, where we think all technologies enable and constrain in different ways based on their features and how they deploy in a specific context. So there's a bit of work because how we deploy something or describe it or talk about affordances is going to depend on who is using it and what they're wanting to do with it. So the affordance framework is an approach to guide discussions and build understanding about potential uses in a structured and helpful way. And you might use language of an affordance framework like request, demand, encourage, discourage, refuse, allow, and similar. For example, if we were talking about a model, we could say, oh, using this model encourages compute speed. Or we might say, this model demands certain libraries. Or this model allows integration with GIS systems. Or it allows for flexible programming of some of the parameters. Oh, but it discourages large ensembles running on a desktop machine in your office. You're going to need a cloud server. So you can imagine if you take this into a bank and they're wanting to use a model, but they're wanting to run it on a desktop computer, knowing those affordances in that context are important. Whereas if you take the same conversation about model use to somebody at a university where they have lots of compute available, well, they might not find that the same constraint that someone else does. So this helps us direct people to some of the more helpful affordances that we might have with our models, is to just take them through that structured type of discussion. And then this was my absolute favorite, signifiers. And hopefully it's empowering to you more broadly than just in statistical models. But if you have the same problem over and over again with a device or a model or interpreting it, maybe it isn't you. Maybe it's just designed kind of wrong or poorly. We got a new TV and the remote has a wheel on it, and I just assumed it was going to work like an Apple remote, and it did not. It was not useful because it didn't align with my cognitive model of how wheels should work, and it didn't have the buttons that I was familiar with on traditional remotes. It was a piece of junk. It was poorly designed, and you know what? I had a feeling about it, and it wasn't good. I was very angry. It didn't have what I was expecting for signifiers. So affordances are about what actions are possible. Signifiers tell us where and how an action should take place. So it turns out there's a brand name version of the toy I got for my daughter, and it has an arrow on it to tell you what direction you're supposed to add the elastic bands. Epiphany. It wasn't my fault. It was designed badly, but I could add this signifier myself, and suddenly school holidays became just a little bit easier. And just to encourage us as statisticians, in explainable AI literature, they quite often acknowledge that visualizations are better than text lab, but they don't go into much detail about how to make a good one. And I note that in statistics and also in machine learning, we quite often use signifiers already in some of the graphics that we build. Design language is just giving us a formalizing process and a language to talk about why certain visualizations are better than others, or so we can think about how to convey specific bits of information that don't seem to be getting across. So you can see in here, we've conveyed lots of information that we've got two groups, and they're in different colors. We've signified that. We've signified the confidence interval differently than the data. So we've signified that there's data, that we have uncertainty, that we have a trend line. And there's my predictive line that goes with my picture. But there's quite a lot of signifiers that we're already using. Yeah, we do a good job. I'll leave it there. All right, and conceptual models, which is what we're going to extend into graph thinking, assuming I've still got time, is conceptual models are an explanation, often highly simplified, of how something works. It does not need to be complete or even accurate, as long as it is useful. Now, I struggle with this one a little bit because I like to over-explain things in stats because I love it, it's so cool and elegant. But sometimes I do have to take a step back, and sometimes I think it is really important that as a collective we take a step back and think, does it need to be this complicated for how it's going to be used? Or can people use it effectively if I give them less information, but they can interrogate it in a way that allows them to feel empowered with the system? So conceptual models, there's been lots of duffs with these, with ChatGPT coming out, and this was a recent headline that said, this US lawyer used ChatGPT to research a legal brief with embarrassing results. We could all learn from his error. And in this case, I think he'd gotten ChatGPT to just write the legal brief and it had hallucinated and made up stuff. And the judge happened to notice. Yes, it is an affordance of ChatGPT that it will write a legal brief for you. But the conceptual model of this person was wrong, right? For me as a statistician, I know that it's just a probabilistic remixing of stuff and that it's not necessarily going to be the truth. But that's not necessarily known that well out in society. So perhaps ChatGPT needs some signifiers to help people know, it does hallucinate, or make those things more clear. We need to improve people's conceptual understanding of these types of models so we can avoid issues in headlines like this one and some of the ethical implications that come, especially when the judge doesn't notice that it's all made up case law. All right, and this is another conceptual one, just bringing it back to statistics as a context. This one comes up to me at least once a year. Somebody has an equation for a line and they're really upset because their supervisor or their manager or somebody, this doesn't happen to statisticians, by the way, it's always in applied science. And they say, well, I need to be able to explain the difference between groups and all I've got is the equation for a line. So they say I need to run 2 regressions because they've got this conceptual model of I have the equation of a line and this is a line, right? And I always get to explain to them, and it makes me feel really good, right? Because I'm pretty good at explaining this. To say, oh, no, you've actually got 2 lines and you can calculate those differences and you have everything that you want. So we just needed to expand our conceptual model a little bit, and we can do that with a nice graph, which we've already talked about, that being a really helpful visual tool beyond just the equation of the line where they've gotten kind of stuck on the prediction. And going on to the point that we don't always need to know the inner workings of how things go with models to interrogate them and use them effectively, sometimes we just need to know enough. So I had a friend and he got a new car. Sorry, you can tell it was school holidays and my daughter does like to help me with my presentations. And he got a new electric car. So he's the guy, the computer on wheels, so excited about that. And it had automatic lane detection. Right, and this guy lives next to a highway. So almost like 100% of the time when he gets out of his house to go somewhere, he is having to merge onto a highway and go over a lane. So every time he's trying to make this complex move, you know, the car's going, you're changing lanes. Are you sure you want to change? And he's like, okay, I really love this car, except when I'm trying to merge on the freeway and it's fast and I don't need this on my steering wheel all the time. And he goes, what I don't know is whether the car, which is this AI system on wheels, is it updating the model based on my driving? And after a month, it's going to realize that I do this 3 times a day and it's just going to stop me at this GPS location. Or is it hard-coded in? He didn't care whether it was a regression model or a neural net or whatever it was that was deciding to give him this detection that there was a lane change. He just needed to know, was the model going to update based on his driving and his patterns? So that's what I mean, is sometimes a conceptual model needs to be just enough. He just needed to know enough to know whether the model was updating, but he didn't care what the underlying bones of the model were. So sometimes we need just enough detail. All right, and now I'm going to take you onto the graphs and electricity and stuff, but we're still going to have a little bit of that explainable flavor, I hope, and conceptual model thing. And I'm going to be honest with you, I'm relatively new to the electricity space. Not as new to graphs, but not an expert at them. So I'm on a learning journey, and I'm still figuring out some of the different implications of the different approaches to drawing graphs, and what that might mean to inference and explainability. So from now on, you can assume that I am practicing my learnings, talking to you about them, and I'm also planning to leverage you as a brains trust to help me solve the problems and understand whether the conceptual models really are that different between different approaches. So I thought I'd ask, how many people have worked with graphs before in their math or statistics or career that have some familiarity? Okay, so we've got a couple of people in the room who have familiarity with graphs. I was really daunted, right? Because I was like doing this talk and I didn't know how to do it. And I was looking at graphs. I realized there was some like precocious high school where they were taking graph theory. And I'm like, oh my gosh, if everybody took this in high school, they're going to think I'm very basic. But we will go through some of the key ideas. So this is a graph. A graph has nodes, which are the round bits, and edges, which are the straight bits. They can also be called arcs. The graph I'm showing you happens to be a directional graph because we can see that the arcs have little arrows pointing in a direction. We can measure things like graph based on these connections, things like centrality, which is the number of edges on each node. And quite often in graphs, the nodes and the edges represent things that exist in our world, whether it's relationships between people or stuff in the universe. All right, and in this case, I'm representing you a small electrical network graph, where D are demand nodes, so they're like houses with people using the power, and the numbers 1 through 5 are electrical buses, so they're part of making the circuit that allows the power to flow to our homes. And T represents wind turbines who are going to put power onto our electrical network. And then the arrows and edges represent the flow of electricity. And you'll note that up in the top right of my graph between node 1 and demand D, there's one node that's bidirectional because somebody's got solar on their house. Everybody happy with my explanation of electrical? Okay. All right, and we can also represent these graphs as a matrix, right, to represent the connections between them. Because this is a directed graph, we look at it and we say, node 1 connects to node 2. Can people, and I hope that people can see my mouse online. And so we have a 1 there to say, yep, there's a connection there. And then we have node 2 connecting to node 3. But it doesn't go the reverse direction because the arrow is only going one way on those nodes. And I note I'm just doing the buses, so the numbers 1, 2, 3, 4, 5, so it fit nicely on my PowerPoint slide. But you get the idea that we can draw these as graphs and then we can do operations on those numbers. And more recently, I've been learning about different ways to draw graphs. I'm now going to choke on water in front of a crowd of people. So there's the traditional way we draw graphs where we talked about the stuff in the universe. But more recently, I've been learning about something called a heterofunctional graph, where graphs are drawn based on function. So I'm going to start you off here. Oh, do I want to go here? Yeah, sure. Okay, so I'm going to start you off here. This is my stuff in the world. Okay, everything we see here are nouns. quite often both the edges and the nodes in our graph represent things or nouns in the world, at least conceptually, tying it back to the conceptual models we were talking about earlier. So my dots that I'm going to add to my graph represent different systems that interface with the electrical system or with each other. So in this case, we have edges and nodes that are representing aspects of water, electrical, residential, and transport systems, residential and commercial areas. Everybody buying my story? So we have electrical is yellow and water is blue, my house is pink, and Cyro site is gray. Right. And then we can add the stuff in, right? We can give it some notation. In heterofunctional graphs, it's come out of something called model-based systems engineering, which is come out of the aerospace industry. Because if you think of making a spaceship, there's lots that needs to coordinate. There's a propulsion model, a structural model, control systems, electrical systems, air systems, and all of those things have to be coupled and synchronized and operate through launch, through turbulence in the air, through zero gravity of space. All of those systems have to work together in a coupled way. And I postulate, and we're trying to get more of this in the energy networks, energy, especially when we're trying to integrate renewables, isn't that different. We have new types of generation, we have transport of energy, we have market models that need to incorporate that different way that we're generating energy that isn't just about burning stuff, and we have the humans that interact with it, for example. And in model-based systems engineering, because it's kind of engineering-y, it's got some engineering-y concepts and pictures, I'm going to try and stay away from that until the end of the talk. So I will argue to you that there is a context relevance on the last slide that I think I'll show you, because engineers like it to look a certain way, and I like pretty pictures. But in heterofunctional graph theory, which is part of model-based systems engineering, there's a focus on both the things and the functions. So instead of just being nouns, 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 you're adding some verbs in there. You have a noun that does a thing, which is kind of how we think, right? We think in sentences. And so what I want you to do as we go through the next slide is to think about what are ways that this might change the cognitive model that we have of the graphs that we draw. And we can think about it in things like, what is the resilience of the system? And is it just easier to draw a graph when we think about it in terms of what things do and what their operations are rather than the nouns that they represent? And I am genuinely looking for feedback on that. I don't know the answers. I'm still puzzling my way through some of the implications. So back to my drawing. Okay, now we've added on some of the things that we can do with our electrical wires, right? So we generate electricity on the panels. We transport power to the water treatment plant to treat our water. We transport power to residential areas. We treat our water. We transport that water to homes. In my house, lots of stuff is going to happen. So I've got the water. I can use the water in my home. I can park my EV. I'm a bit fancy. I'm going to pretend I have an EV. I can charge my EV at home. I can discharge my EV by driving to work on the transport system. And I can park my EV at work and take it back home again, discharging it again. And we're focusing on the EV there because it's part of the electrical system. And then we do some reflexive actions and we get this graph, which would be the heterofunctional graph, which is focusing on the function. So we've added, the big thing that we've added is quite a few extra nodes to this graph because we're adding nodes for some of the functions that are happening. And I've got a question for you, which might be, I'm running short of time, which might be discussed at dinner with this group. But what happens to function, if I go back here and we can see the full picture, what happens to the function of our system if we knock out the treat water node? Okay, and what I'd hope you notice are things like we lose the demand for electricity on that node. We don't have any water to transport, and devastating for me, I won't be able to take a shower that night because there's no water left in the system. So that thinking about function, I think, actually ties quite nicely to thinking about the resilience of systems and networks, which has become a big deal post-COVID. All right. And to think about this in the context of network resilience, I just had a question for the crowd, and I am really hoping somebody puts up their hand. Is there anybody in this room who either has solar panels on their house or batteries, or they have, oh, great. Okay, why did you do it?
Mainly because of environmental concerns, but also we don't get electricity.
Right. Okay. So some of it was environmental concerns, and some of it is we don't get electricity bills. Why don't you get electricity bills? How about you? What was your reasoning? Was it similar?
Probably. Yeah.
Yeah, probably similar. So you have this idea that you're almost off grid, right? You're self-sufficient. There's something resilient about being self-sufficient and something dignified about that. Right, so I'm asking why. I should flip that over sooner. All right, so it's this resilience. Some part of why people get solar panels is because they are doomsday preppers, or because they just want to have that sense of resilience and self-sufficiency. And one of the ways, and like this is like published in Nature, that this has been analyzed looking at it, so countrywide scale, looking at countries like the United States, is degree centrality as a proxy for resilience. Because the more connected your grid is going to be, the more resilient it is. Because if you knock off one connection, darn it, there's lots more to cover the gap. So that's one of the ways that we increase resilience in networks, is to increase the number of connections. So unmeshed, that's the network I showed you earlier, and then there's a meshed network. But now people are thinking about networks in this different way, right? I can add solar power and batteries to my house. So we would think that that would increase resilience, increase that centrality. But if we take centrality to be our resilience measure, my black line is what happens when I mesh. It's behaving as I expect. As I increase the meshing of my network, I increase resilience. Right, but when I think of the traditional graph, so that first graph I showed you where my house was just one node with a simple set of connections, what happens to my graph, the topography of it? Do I add a connection when I add a solar panel? And the answer is no, it stays essentially the same. And so resilience doesn't increase as you add solar panels and batteries, and that's a little bit unsatisfying. So let's try it with heterofunctional graph theory, right? Let's try it where we've got all of those extra connections and my house is split up into 3 and it can have this extra functionality that I add with my solar panel and my battery. Are we going to do better? And the answer is kind of, if I'm using node centrality as my measure. Here we can see, again, we have, I meant to do that. We can see that with meshing, we still have that increase that we would expect to see with resilience because that's graph theory and it meets common sense. I'm now having batteries give me quite a large effect. It's increasing my resilience. I have batteries. And if I add solar panels, I get a little bit of a resilience increase. How many people believe that this is true? That that's all of the resilience uptake that you get when you add a solar panel? Does that meet our sense of common sense and intuition? No, right? A couple people have said no. A couple people are like, I don't know, I haven't worked with electricity before. Your intuition is right. This isn't satisfying to electrical engineers either. It's a little bit of an improvement, what we're getting with solar PV, but there's something really missing around how we're measuring the importance of nodes and the additions we're making to our graph in terms of resilience measure. So I pose that there's like a big opportunity to come up with new measures in this area and figure out how they distribute because they're not perfect. And I note that if you go to something, and if you think of node centrality, it's looking at how many nodes one away that you connect to. If you look at the full path, right, all of the different paths that a node could connect to, we do a little bit better in terms of solar panels. This is actual results from when they ran it across America. Looking at their energy system, but this is a different importance measure. But I'm not 100% sure I'm convinced in my mind whether I think storage should do more than solar panels or solar panels should do more than storage, where storage is batteries. And I think there's opportunities to come up with other potential measures to sort of assess different aspects of resilience in these graphs when we think about the function we want to have in our lives and the resilience that we believe that we should get from putting more of these renewables at the residential level. But I just think it's quite interesting to think about. When I first came into the heterofunctional graphs, I was like, yeah, whatever, it's a graph, I can do the same measures, it doesn't make a big difference. It's kind of nice that it's got this cognitive model that I'm writing sentences, but it's only recently that I've understood how different the inference is that you get when you change, you're adding quite a lot of new connections. When you're adding a battery, right? You've got 2 connections that can charge and discharge and connect to the network. That's 3 connections for every battery. So that increases resilience. Solar panels also increase resilience, but we're still only connecting them at one node. So I think there's still work to be done both in how we draw the graphs and define the function, and also how we measure the importance of some of these different additions. Yeah, that's exactly what I said to you. Are there other measures of centrality that we should be developing? And is there something new that we could be thinking about, which is the uncertainty that's associated with some of those measures of centrality? And I promised you a really engineering-y slide to finish off the talk. So here it is, my really engineering-y slide. So this is a mapping of the Australian energy system in all of its heterofunctional graph engineering look glory. It is a bit more complicated graph than we've been talking about, and it is quite at a high level of the system. But it's a bit of fun. We can think about it as sources. So we've got natural water that is involved with the system, domestic production, imports. Moving on to the different systems, we have the systems that transport and burn and do all the stuff with natural gas or hydrogen or water. And then we get these lovely outputs. So that's a bit of fun. This is not my slide, but I like it. So you get to see the engineering system. And I know that I think, I've talked a bit about graphs and graph theory and centrality and those measures. I think there's a lot of opportunities in graphs like this as well to think about information flows and interoperability, because we can think of each of those connection points of, electricity to water to hydrogen or something like that. You need to consider the backdrop of where and when those things are occurring and how they're monitored, and also the geography of how they're located. And that starts to think about, do we have the data that we need to drive our understanding of the system, and ties into things like fair data principles, which is data that is findable. I'm going to get this wrong because I'm standing in front of a crowd. Findable. Somebody's got it. Go, Kate. Accessible, interoperable, and reusable, right? Yes, okay. So I think that we can use these sorts of graph models to sort of track the data flows and the data usage and our needs. So that's, I think, another big opportunity for statistics in that energy system space. But we are at time and I am hungry, so I will wrap it up and take a few questions. So basically, there's a lot of science areas that have captured public attention recently, and I'm including energy transition and ChatGPT and foundational model, where statistical ideas have a lot of relevance. So that's the ethical AI, that design thinking of model development and explainability, which is becoming bigger, and things like energy transformation. And I think there is a lot of cross-pollination between our domain as statisticians and these other domains that could lead to some value developments, both in statistical literature, but also in other domains and in broader society. And there's also the opportunity to find some unexpected allies. I find thinkers particularly aligned with statisticians, and I think I've said it to statistical groups before. There are always the ones that are asking, but have we actually sampled the people that we're trying to represent in this system? They're always first to ask that question because there's more of them. But I'm always right there in there going, that's correct. We need to think about those sampling frames. And it's been good fun to cross-pollinate ideas with them. So that's my wrap up. A big thank you for inviting me tonight. I had a lot of fun thinking about this talk and what I would share with you, along with a little bit of terror as I choked on my water earlier. But I'm hoping, people have some questions or feedback around heterofunctional graphs and energy and design thinking and all the mishmash that you've gotten tonight.
We'll start from in the room. Is there any questions or comments?
I've got one. Well, probably a couple. Thanks for a very stimulating talk. If I go back to resilience, since that's the last bit.
Sure, yeah. Okay, well, we'll do this so people can hear, and I might repeat the question for the online audience, or will they hear it from here? Okay.
Yeah, am I being heard online?
If somebody can give us a thumbs up if you can hear Alan.
It's down low. Sorry.
Yeah, that's a thumbs up. Yeah.
Okay.
Great, thank you. Resilience. I would have thought that the concept of resilience I'd be interested in is whether I can deliver sufficient electricity, say, that's what we're talking about, rather than how well connected the graph is. Because that seems to me to be locking into a metaphor. I consider it a useful thing to know.
Yeah.
But is that really capturing that?
No, I don't think so. I think it's capturing a part of resilience, right? A piece of resilience. I figure there's more to uncover and really think through in terms of we're still figuring out how all of these things are going to operate together with virtual power plants and things. But I think there's a big opportunity to think about resilience with different measures, especially focusing, because you're kind of on those edge nodes of the graph in homes when you're adding solar panels and stuff, and you're not at that central node where you've got gas coming into an electrical generation thing with lots of feeders coming off. So it's a very different paradigm that we're moving into. So I think we need to do different thinking about resilience, absolutely. I don't have the answers yet.
No.
Yeah, okay.
If I just follow up with that, does that mean that, is that all right?
Yeah, try it. Yeah, some people say they can't hear very well. So.
Oh. It could be their problem.
Yeah.
There seems to me to be a problem that requires simulation, systematic simulation of complicated systems to see what a critical failure points, if you like. More than that, obviously.
Yeah, I think, yes, I agree. And I think it's just at the cusp. And this is, again, like, I didn't go into all of the things you could do in energy. If you look at IEEE, they have a whole bunch of, demonstration networks of various sizes, which my 5-bus networks is the smallest of those, all the way up to much bigger scale things. And that is one of the things we'd like to do, is look at simulation around that in the context of what's actually happening from a physics perspective as you add these different things, or you have days with different weather, for example. So that's sort of in progress work, but we're starting from a very small space. When you look at what they've done across America, looking at centrality, they've sort of assumed a lot about what's happening based on sort of historic top-down. We have a big generator and it flows down through the energy system. So I don't know the answers yet, but I agree with you. Simulation will be very valuable, and I don't want to be the only one doing it because I'm not smart enough.
We have one question online.
Yeah.
Says, thank you for the talk. It was very informative. I was wondering if you have considered a way to add time to these MBSE graphs.
Have we considered a way to add time to the MBSE graphs? And the answer is not in a very formal way. I have really good lunchtime conversations with a colleague of mine. Hopefully it might be my colleague. No, not Hesper. But Hesper, if you're interested in that, shoot me an email, because I have a friend who's very interested in that sort of spatiotemporal context and evolution of graphs and how you integrate that information. So we should definitely talk more, because it is a very interesting developing area.